Good morning, sir.
Yeah. So is the screen visible?
Yes, sir.
Okay, so this is what we had to do. Prim's algorithm. Okay, Prim's algorithm is again to find minimum weight spanning tree. Okay, but this is different from Kruskal's algorithm. Alright, so this was one example for Kruskal's algorithm. So let's start with this example itself. Okay, so give me 1 second. I'll show it in this example itself. Okay, so let me draw this graph once again quickly. So the graph looks like this. We have an edge, we have a vertex here. Okay, so this is the graph, and let me also put the weights here. 9, 6, 4, 3, 11, 10, 2, 1, 7, 4, 3, 2, 1, 6, 8, 1, 5, 1. The remaining this adjustment. That's very cute. Okay, all the edges have received their weights. Okay, so Prim's algorithm now, in order to find minimum spanning tree, proceeds as follows. Okay, so once again, so if you notice, Kruskal's algorithm was simply a greedy kind of algorithm, right? You are going on finding minimum, minimum edge, and so on. Okay, in Prim's algorithm, we will use depth first search in a certain way. Okay, not exactly depth first search, but some sort of a variant of that. Okay, so we'll try to grow a minimum spanning tree. So what is that? Take an edge with minimum weight. Okay, start with an edge of minimum weight. So here, let's start with one edge with minimum weight. Let's start with this one. That's the first step. Okay. Now look at the vertices incident on that edge only, not everything else. Look at the vertices incident on that edge. Okay. Now look at the edges that come out of each of those. Okay. So from the right vertex 2 more edges are going out. From the left vertex, 3 more edges are going out, right? So these are the edges incident on this chosen edge. Okay, so from the edges that are incident on this edge, pick the one with the minimum weight. So you're not, the difference from Kruskal's algorithm is you are not looking at all the remaining edges and picking the minimum. Instead, you are looking at edges that are incident on this chosen edge, only those edges, and picking the one with minimum weight. Okay, so this edge has weight 1. Which are the edges incident on this? So there are 3 going out from the left side, 2 going out from the right side. Okay, if you look at the weights, the minimum weight edge is an edge of weight 1, this one. Okay. Oh, sorry. I wrote a weight twice, so we don't have this weight. We only have weight 1. So this one. Alright, now what do? Now you have 2 edges. Now you have 2 edges chosen. Now look at all the edges that are incident to just these 2 edges. You understand how we are going to do? Look at the vertices on these 2 edges and look at all the edges connecting to only those vertices and no other edges. Okay, pick the one with minimum weight. Once again, now without making cycles. Cycles we always have to avoid every time. Okay, whenever we choose an edge. So look at only those edges which are incident on these chosen 2 and pick the one with minimum weight. So if you look at this, there are 3 vertices on these 2 edges. The leftmost vertex, there are 2 more edges, weight 2, weight 6. The in-between vertex, there are again 2 more edges, weight 10, weight 5. The right-hand vertex, again there are 2 edges, weight 2, weight 8. So the minimum weight is 2. So let's pick one edge among these of the minimum weight 2. So let me pick this one. Is that okay? Right? Now what do? Now repeat this. Look at edges incident on only these edges. All the edges connected to only these edges. One of these 3 edges now. And pick the one with minimum weight. So now there are weight 9, weight 6, there is weight 10, weight 5, weight 2 and weight 8. So the minimum weight choice is now this one. Okay, so let me also keep drawing as we used to do before. So first we chose this edge, then we chose this edge, then we chose this edge, and then we chose this edge. Weight 1, weight 1, weight 2, weight 2. Alright. Now look at edges incident on these. So we have weight 9, weight 6, and then weight 5 is not allowed, this edge, because it will create a cycle. So this is anyways not there. We have weight 10, we have weight 8 going on. Okay. So 9, 6, 10, 8, minimum is 6. So we'll choose this one. Okay, so now we introduce this one. Weight 6. Now repeat. Now just go on repeating. So among the edges incident on all of these, which is the one with minimum weight? Okay. Oh, there's a mistake. Sorry. This one won't come, no? So if you look at this, there is weight 6, weight 9, but this edge, the edge with weight 2, the long edge, this is incident on weight 2, weight 7, weight 11. So this is the minimum. Okay, so yeah. Now look at all the incident edges on these edges and you will find that the minimum is this one edge, weight 1. So again, look at the ones incident on all of them without forming cycle. There will be a unique choice. You will find that this is the minimum edge. So like this. Okay. Now look at edges instead in all of these and pick the one with minimum weight. Okay. So we have weight 9, weight 6, we have weight 10, weight 8, weight 2, weight 3, weight 7, sorry, weight 4. So weight 2 is the minimum. This one is the minimum. Okay. So now this is the minimum. Now if you look at all of these, now you cannot choose weight 4 or weight 3. These two edges are out of question because they will form cycles. So those are out. What else remains? You included this new edge. Incident to that, there is this edge of weight 1. So automatically this becomes the minimum weight. Okay. What else now? Let's look at this. Which all edges do you have? Now you cannot have weight 4, weight 7, weight 3. They will all form cycles. You have weight 9 available, weight 6 this way available. Okay, weight 8 you can't choose, weight 10, weight 5. So number of choices is reducing because the number of edges is reducing. Weight 5 is also not allowed. So you have 9, 6, 10, 11 and 6 to choose from. Okay, so the minimum in this case will become this. I got made two choices, either this edge of weight 6 or this edge of weight 6, this curve of weight 6. Any one will do. I made this choice. The moment we choose that, we have now this among the remaining edges. Now there is a unique choice of minimum weight 3. Okay. Now if you check, every vertex has been covered. If you just check, no vertex is remaining. Every vertex is now lying on at least one of the edges that we have already chosen. So this is a spanning tree. Okay, the algorithm stops here. This is a spanning tree, and it will be spanning tree of minimum weight. Okay, the algorithm stops here. It's a spanning tree of minimum weight. So is this clear, everyone? Prim's algorithm, just a small variant. Instead of going on picking minimum all the time, as in Kruskal, you are looking at only those edges which are connected to edges that you have chosen before. The rest of the idea is the same. Again, pick minimum weight edge while making sure that there are no cycles. That's all. That is Prim's algorithm. Is that clear, everybody? So now just take 5 minutes and just look at this and tell me if you don't understand something. Okay, just look at what we have done, trace back these steps, and if you don't understand something, just ask immediately. All right. So is this clear, everyone?
सर वो हमने यहाँ से वर्टेक्स क्यों लिया है?
कहाँ
ये
से?
1 से लेके पूरा 2 से लेके पूरा 1 तक, बाद में बीच में सारा वर्टेक्स छोड़ दिया है, बीच का वर्टेक्स
बीच का
डायग्राम।
कोई वर्टेक्स छूटा नहीं ना. Every vertex is belonging to at least one pink edge. सब वर्टेक्स कवर्ड है. कौन सा
मीन्स
वाला?
सर दैट 2 edges only half you have taken, means, and rest of edges are remaining as it is. Why, sir?
So you only want spanning tree, no? We stopped here because we have already got a spanning tree. It's a tree which is a subset of edges. There are no cycles in between, and every vertex has been covered by at least one edge. So we stop. We don't
Okay,
want to
sir.
cover all edges, no? We only want a spanning tree. Right? We wanted a spanning tree with minimum weight. The sum of weights on the edges should be as small as possible. So
Yes,
minimum
sir.
weight spanning
Understood.
tree. Yeah, yeah. Alright, so that is that, and there's only one more small thing remaining to do, which is very very easy actually. So let's do that. It's something called topological sorting. Okay, so what is a topological sorting? So have you all seen directed graphs now, by now?
No, sir.
You've not seen directed graph?
सर उसके बाद से लेक्चर्स नहीं हुए हमारे, मतलब ग्राफ का
क्यों, क्या हुआ?
स्पैनिंग ट्री के. पता नहीं सर, मैम का भी लेक्चर नहीं हुआ काफी टाइम से.
अच्छा. Okay. ठीक है, तो टोपोलॉजिकल सॉर्ट लास्ट में देखते हैं. Let me give you something, a quick application of BFS. Okay. एक छोटा सा एप्लीकेशन है BFS का, एप्लीकेशन ऑफ BFS. तो हमने ब्रेड्थ फर्स्ट सर्च और डेप्थ फर्स्ट सर्च देखा है ना, BFS एंड DFS, राइट? इन दोनों का एक एक एप्लीकेशन देखना है. ओके, BFS का एक एप्लीकेशन है, DFS का एक एप्लीकेशन. ऑलराइट, सो BFS का एप्लीकेशन बहुत ही सिंपल है. Okay, so what is it? So the application is shortest path between vertices. Shortest path between vertices. Okay, path का definition पता है ना सबको? path पता है सबको? path in a graph.
Yes.
Okay. So what is the shortest path? Path with the smallest possible number of edges. Okay, for instance, if you have a vertex of this kind, if you have a graph of this kind, okay, these are two vertices A and B. What is the shortest part between the two?
नीचे वाला अगर edge लिया तो
Okay, so the length of
directly
the
from
path
A
is
to B.
just the number of edges. So the path with the smallest number of edges. So in this case, this is the shortest path, नीचे वाली, because it has only one edge. Shortest path between A and B. Okay. What if I give you something else? What if I give you C and D? What is the shortest path?
So between what?
Between C and D. So between A and D,
C
we have
to
seen
A.
this is the shortest path.
C to A and from A to B. A to D.
Yeah, okay. So that's the shortest path. This. So this and then this. Okay, that is the shortest path. Okay, so now you understand what is the shortest path. So now the question is, how do you find out shortest path between any two vertices of any graph? Okay, I'll give you a graph and I'll give you 2 points. The question is, how do you find the shortest path between the two vertices?
We try to find minimum number of edges which is required to reach
Yeah, that
between
is
the
a
two vertices.
definition. That is the definition. But how do you construct a path? Okay, that's the question. So the quick application of BFS. Okay, so if you see BFS, let's try to apply BFS on this one. Okay, so if I start with BFS on this edge, starting with let's say, so okay, suppose I want to find shortest path between A and B. Okay, we know this is the shortest path. Now let me just show you how this happens. Okay, I'll show it in this diagram itself. All right, so I want to find shortest path between A and B. So question 1, shortest path between A and B. So here's the thing. You want to apply BFS. Now remember BFS, okay? If it's not clear, go back and revise what BFS is. For BFS, we start with an arbitrary vertex and then go on picking as many edges as possible incident on that vertex, while making sure that there are no cycles. So when you want to find shortest path between A and B, okay, you will either start with A or B. Okay, any one is fine, but you have to start with either A or B, not any other vertex. So let me start with A, and then let me apply BFS. So if I apply BFS, what do I get? First step of BFS will give me this edge, this edge, and this edge. Okay. Alright. Next step of BFS will give me, from here I'll go here, and that's it. Okay. Every vertex has been covered. So this is a minimum weight spanning tree. This blue edges, light blue edges, 1, 2, 3, 4. Now in this BFS, of course B has been covered once, right? But it's a tree, right? It's a spanning tree. So given any two vertices, there is a unique path. Okay. So the path between A and B in the BFS tree is the shortest path. Do you see that? There is only one path between A and B in the BFS tree. And that path is exactly the shortest path between A and B. Is that okay? Let's repeat that. Let's repeat that for some other vertex. Let's repeat it for some other color. Okay. Let's repeat it for C. Okay. So I want to now find the shortest path between C and D. Okay. So let me start with vertex C or D, but not anything else. I'll start with vertex C. Now apply BFS. When I apply BFS using C, starting with C, the first step will cover these two edges. That's it. In the next step, I'll look at A and then cover this edge. I'll also cover this edge. And the BFS also, BFS, this one also stops. Okay. Once again, I've got the same spanning tree. But now, the shortest part between C and D is the path between C and D in this BFS tree, which is C to A and A to D. Exactly that part. You see? So,
Yes,
apply BFS. When you apply BFS, you'll get a spanning tree. In that spanning tree, between any two pairs of vertices, there is a unique path. That will be the shortest path between those two vertices. Okay? Is that clear, everyone? That's all. That's the application of BFS to finding shortest path. Okay, so the BFS tree will always contain a path with the smallest possible length for any two pairs of vertices. Okay, it's not true with DFS. It is not true for depth first search. This is true for breadth first search only for BFS. Okay, DFS is used for something else. Okay, that is what I was going to start topological sort, but I want a directed graph. So anyways, what I'll do is directed graph. I don't want to do it in a lecture setting. It will take a little bit of time. So today I'll post a small introduction on directed graphs. Okay, look at this video. I'll post it in some time. Look at that video before we meet tomorrow. Okay, so tomorrow we will meet at 8 o'clock. Okay, correct at 8 o'clock. So how much time do you have until the next class? What is the time now?
9:07.
When is your class starting? Did your next class start?
10 o'clock.
10 o'clock.
Yes, sir.
Okay. Okay, so then in that case, I will also do the other part. So you might take a 2-minute break. Okay, I'll also just drink some water and come back. Let's also do DFS application. That is very short actually. Only takes some 10-15 minutes. Okay, I just have to show you what a directed graph is. So let's do that also. Okay, so just take a 2-minute break. I'll also come back and then we'll complete this. And if we complete this, our syllabus is done. Okay, then we only have to do tutorials and problems, nothing else. This is the only part that was remaining. Application of BFS and DFS. We already done BFS. I'll also complete DFS. So we'll be done with the syllabus. Okay, so take a 2-minute break and we'll come. Okay, so let's continue. So the small part that remains is, now it's an application of DFS. Okay, and this is called topological sorting. Okay, topological sorting. What does this mean? Okay, so let's start with some graph. Now the difference is it's a directed graph. So what's a directed graph? So let me first draw a graph. Okay, we have this graph. Directed graph simply means between any two vertices, when you have the edges, they are not just simple edges, they have a direction. They are either going one way or the other way. Is that okay? That's all it means. They are going all either one way or the other way. You understand? You see, these are the arrows. Okay, this is a directed graph. The other ones that you have seen, they are called undirected graphs. The edges don't have a direction. Here, the edges have a direction. It's a directed graph. Is that okay? That's all. So what is a topological sort? So now let me first show you an example. Okay. So now we will need to label the vertices also. So let's give it some names: A, B, C, D, E, F, H. Alright. So these are the vertices and there are edges between them. The edges have some directions. That is fine. Now let me write down a list for you. Okay. A listing of all the vertices. Alright. I'll write down a listing of all vertices. So I'll first write it down and then I'll explain what it is. So start A. Okay, there are 8 vertices here, and I have written all these vertices here. Okay. Oh, sorry. Small mistake. Sorry. Small mistake. One second. I just have to change this order. Okay, so yeah. Alright, so the first thing to check here is that this graph is, it has no directed cycle. Everybody knows what a cycle is, right? A cycle in a graph.
Yes, sir.
Directed cycle means it looks like this, you know. So this is an example of a cycle. Directed cycle means, you know, it's like either clockwise or anti-clockwise, all same directions, and then following that directions you have cycle. That's the meaning of a directed cycle. Okay, so this graph, for example, will not have any, does not have any directed cycles. You can check. Okay, it has no directed cycles. Okay. So now what do you do? So look at these pink edges. Okay, so in the listing there are sorry, the order is preserved. Okay, in the listing the order is preserved. I missed one vertex E. I missed writing H. Sorry. So in the listing, the order is preserved. What does that mean by order is preserved? Okay. So this is a listing of all the vertices. Take any vertex and take any vertex to its right. There, the edge between those two vertices is always directed forward. For example, A to B, the edge is directed forward. Okay. C to E, the edge is directed forward. Right. F to G, edge is directed forward. Okay, G to H, it is directed backwards, that is fine, but H is already covered, sorry, H was the singleton, the last vertex, so it doesn't really matter. G has already been covered by F. Okay, so when you read from left to right, the directions are preserved at least by one pair for every vertex. Okay, for instance, if you pick F, either E to F or F to G, one of these two at least should be true. Okay, that's the idea. So in the listing, the order is preserved. Okay, so this listing is called a topological sorting. Of vertices. Okay, topological, why? Because of this property, the ordering is preserved. Okay, that's why it's called a topological sorting of the vertices. Now the question is, if I give you a graph, how will you obtain a topological sort? Okay, how will you obtain a topological sorting? Alright, now let me show you here itself as to how I will obtain a topological sorting. We will obtain it by applying DFS. Okay, DFS, but by also respecting the directions. Okay, so in this case, I'll start with the vertex A. I can start with any one vertex, but I should start with a vertex that has maximum number of edges going outside. Okay, maximum number of edges going outwards, not coming into the vertex, going out of the vertex. So A is that candidate in this case. Okay, there could be multiple, in which case you pick any one. Okay, so pick the one with maximum number of vertices going outwards and start from there. Now apply DFS to A. But while applying DFS, you will only look at edges going forward, forward, forward. You will not include edges going backwards. That is the only change here. Okay, so you have to respect the direction. So with A, DFS will carry me to, it will give me B. I'll choose B. And the moment I add vertices, I'll keep on adding it to this list. So next is B, I wrote down B. From B, I choose F. So I wrote down F. From F, again I'm looking forward, so I'll choose D. I won't, okay, arbitrary choice. I'm not choosing E because E edge is directed the other way around. Okay, so DFS, this is the change. If it was undirected, I could have chosen E as well after F. But it's directed graph and I'm applying DFS, so I cannot choose E anymore. I can choose only D. So I choose D. And from D, now if I see, there are no more edges going forward. So DFS stops here. What do I do then in DFS? Backtrack. Remember, you will backtrack. Okay, so I think I wrote another listing here, so I'll write it down here. So A, B, F, D. I'll backtrack. I'm at F. Then I'm again trying to go forward, so I'll choose G. From G, can I go forward? No. So I'll backtrack. Now I'll again backtrack. From B, can I go forward? No. I'll again backtrack. From A, can I go forward now? Yes, I can go to C. So I'll choose C. From C, can I go forward? I only have one choice, E. So I'll choose E. Okay. Now can I go forward? No, I'm done. Okay. Even after backtracking, I cannot do anything. But so I'll stop here and then look at the remaining vertices. Now in the remaining vertex, there's only one H. So I'll write down H.
सर ये बैक ट्रैक वाला एक और बार एक्सप्लेन करेंगे क्या?
हाँ,
तो बैक ट्रैक वाला में
बैक ट्रैक वही था ना. सो नॉर्मल DFS में जब all the neighbors are already covered, from that vertex I cannot choose any other new vertex. So I'll go one step behind the previous choice and then look forward from there, right? In this case, when I'm backtracking, I'm also respecting the direction. That's all. So for example, अभी A, B, F, D, D से आगे जाने के लिए नया vertex कुछ नहीं है. All the edges are coming towards D. There is no edge going out of D to a new vertex. So I'll go to the previous choice, the choice I made just before D, which is F. Right? Now from F, is there any other way to go forward and choose a new vertex? Yes, that is G. I went from F to D. From D, I cannot go forward. So I come back one step, back to F. From here, F, I can again go another step ahead in another direction and choose G. That is backtracking. Okay. Now from G again, I cannot go ahead. So I go back one step to F. Now from F, I cannot go in another new direction. There is no more new direction. So I'll go back to B, the previous choice. The choice before F, that is B. Just in this listing, choice before F is B. From B again, I cannot go anywhere ahead. There is no new vertex. So I go back once again to previous choice, which is A. From A, I can go ahead in a new direction towards C. So I choose C. Then from C, I go to E, and then I stop. Is that clear? So this is plain
सर
DFS.
सी से हम
हाँ बोलो.
सर सी से डी भी जा सकते थे ना, ई को
C से D नहीं गए क्योंकि D ऑलरेडी ले लिया था ना B के बाद.
ओके ओके.
Sorry, F के बाद. We are still looking for spanning tree only. DFS ही तो कर रहे हैं. DFS will always give a spanning tree, no?
Yes sir, yes sir.
DFS ही कर रहे हैं. हाँ. So vertices cannot repeat anyways. And just new vertices have to be added, no? The same vertex cannot repeat. इसलिए. You only look at edges in this case. So normal DFS, you look at edges giving rise to new vertices without forming cycle. DFS directed cycle, sorry, एक minute. DFS directed graph You look for edges going outwards to new vertices without forming directed cycles.
ओके सर, और ए से भी हमने फिर वही लिया ना, मतलब डी को नहीं जा सकते थे बिकॉज इट्स ऑलरेडी कवर्ड, तो ए से हम सी गए फिर.
Correct. He was the only choice. Yeah. Is that okay? So graphs of this kind, no directed cycle. So this is called acyclic directed graph. Okay, acyclic directed graph contains no directed cycle. All right, so that is topological sorting, an application of DFS, but you have to take directed edges. Okay, so with this, formally our syllabus is complete. Okay, syllabus for this course is complete. Now we will do, we will continue with tutorial sessions. We'll do some more problems in the remaining, how much ever time. Exam ka date announced nahi hua hai. So up until the exam date, we will go on solving problem after problem after problem. That's all, nothing else. Okay. So as far as syllabus is concerned, syllabus was only this much. Now you have to really start studying and solve problems. Okay. So yeah, that was it. So right, so I'll stop sharing, and I have one or two announcements before we wrap up today's meeting. So I'll stop sharing. Okay, so the announcement is this: on Thursday again, there is this longer slot possible, right? 9 o'clock and 10 o'clock you don't have anything. So Thursday, today is Monday, so you have two more days, and syllabus is anyways complete. So we will have a quiz on Thursday. Okay, but this quiz will be different. Okay, what will we do on Thursday? Thursday quiz, we will have everything. Okay, it's a long quiz of 1 hour. 1 hour quiz, and there will be 40 questions. Okay, so maybe I should share the screen and write it down. So okay, so Thursday is 20th. So Thursday, which is 20th Jan. A long quiz. Long quiz of 40 questions. 40 marks. Okay. Each question will be of 1 mark. 40 questions, 40 marks. 1 hour duration. You will have 1 hour, and I'll give you 40 questions. So 60 minutes, 40 questions. That is the idea. Is that okay? 60 minutes, 40 questions, full syllabus. Now our tutorials are still going on, so there will be some problems, but I will look at it and I will adjust it according to what tutorial we have done, what we have not done. Accordingly, the questions will be there, so you don't have to worry about that. But as far as the main syllabus is concerned, everything that we have done till today, okay, as of today the syllabus is complete. So full syllabus. Why is this? So you are supposed to take this as practice for final exam. Okay, I don't know what your final exam pattern is, how long it is, or how many questions are there, but I know that it's going to be roughly 1:1.5. Number of questions you will have 1.5 times the time, roughly. Okay. So I just fixed 40 questions, 60 minutes. Okay. So yeah, that is what it will be. So what time should we fix? Let's fix 8 to 9. Okay, 8 to 9 a.m. Be on time. Okay, 8 to 9 means 8 to 9. Okay, don't be late on coming Thursday. Is that okay, everyone?
यस सर. सर फाइनल एग्जाम्स के लिए मतलब हमें कुछ क्वेश्चन बैंक सॉर्ट ऑफ मिलेगा क्या?
नहीं ना, फाइनल एग्जाम क्वेश्चन बैंक का सिस्टम नहीं है अपने पास, तो इसलिए आपके लिए मैं इतना तो करूँगा कि अभी तक जितने भी क्विज और ये फाइनल एग्जाम होने के बाद जितना भी क्विज और फाइनल एग्जाम मिला के जो भी क्वेश्चंस है उनका आंसर सब मैं डाल दूंगा लास्ट में. मैंने शायद आंसर नहीं बताया ना सबका.
हम मतलब फाइनल एग्जाम्स के बाद या उससे पहले?
फाइनल नहीं, मतलब सॉरी, ये वाला लॉन्ग क्विज के बाद.
ओके ओके, यस सर.
हाँ, मेरा मतलब ये थर्सडे के बाद मैं फ्राइडे को ये क्वेश्चंस का पूरा आंसर भी बता दूंगा. आपको मार्क्स पता है ना शायद क्विज 6 तक, तो टोटल इसका भी लॉन्ग क्विज का भी मार्क्स और सबके आंसर्स एक साथ में पीडीएफ में बना के डाल दूंगा. इज दैट ओके? सो हाँ, क्वेश्चन बैंक ऐसा कुछ नहीं है, सॉरी. तो फाइनल एग्जाम में और भी क्वेश्चंस अलग आ सकते हैं ऑब्वियसली. ठीक है. सो वन मोर थिंग, internal marks which is 40. Let me just check. Okay, let me just check. ओके, तो मैं यहाँ नहीं लिखता, नीचे लिखता. टोटल 40 है, तो अभी तक हमने क्या क्या किया है. ओके, सो लेट मी जस्ट सी. 1 2 3 4 5 Okay, so including today's quiz, we have completed 12 quizzes. Of 7 marks each. Okay. In between there were quizzes of 14 marks. For example, अभी पहला 2 क्विज शायद 14 मार्क का था. पिछली बार का क्विज 2 पार्ट में था. Both parts had 7 marks, if you remember. Okay. So all of that is fine. So those parts are thought of as different quizzes. Total we have 12 quizzes of 7 marks each, and I will take best, or rather top 5 scores, and that gives me 35. Okay, total out of 35 marks. ठीक है. उसके बाद है अटेंडेंस बेस्ड out of 5 marks. वो जो भी है. ओके, अटेंडेंस देख के. सो दिस इज टोटल आउट ऑफ, सो ये दोनों ऐड करके ये विल बी योर टोटल आउट ऑफ 40 मार्क्स. दिस इज योर इंटरनल. इतना आपको पता है ना, राइट?
यस सर.
या सो आई एम ऑल्सो गिविंग यू एन ऑप्शन. तो आज से अच्छे से पढ़ाई करो. आपका इंटरनल मार्क्स बेसिकली डिसाइड हो गया है, क्योंकि आज का क्विज मिला के क्विज सब खत्म. अटेंडेंस में आज तक का ही अटेंडेंस देखने वाला हूँ. ठीक है, क्योंकि सिलेबस आज खत्म हुआ है. ट्यूटोरियल वगैरह कोई बात नहीं, ज़्यादा नहीं देखेंगे. आज तक का अटेंडेंस देख के 5 में से आपको अटेंडेंस का भी मार्क्स मिल जाएगा. सो दैट कंप्लीट्स योर इंटरनल आउट ऑफ 40. ओके, नाउ दिस इज द थिंग. लॉन्ग क्विज वॉट एवर यू गेट. सो क्विज out of 40 marks. Okay. Your final internal marks will be maximum out of this internal marks and long quiz. So you had this whole thing of 40 marks, right? आपको roughly idea है आपको कितना मिला है, whatever it is. Study well, study well and give the long quiz on Thursday. If you score more in the long quiz than what you got before out of this 40, I'll give you that as your internal marks. Okay? Is that fine, everybody?
Yes, sir.
Yeah. So yeah, that was the announcement. So Thursday, 8 to 9, we have long quiz, 1 hour, 40 questions, 40 marks. Okay then. So कल मिलते हैं 8 बजे. For now, we only have tutorials, nothing else. Okay. Until whenever exam starts, we'll just continue with tutorials. Okay then. So thank you.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah.